Everybody knows that you can't eat that. You can't eat that, 'cause that is a bet. Okay, so what we're looking at here is current and voltage again. We're going to be looking at some more complicated scenarios, and we're going to be diving deeper into circuits and trying to figure out what voltage drops or currents through individual components of those circuits actually are. So let's take a look at something here, kind of get us moving into this. So let's just set up a circuit where we have two 100 ohm resistors, and we're going to do this once for series and we're going to do them once for parallel. So we've got two 100 ohm resistors in series hooked up to a 24 volt EMF source or some battery, right? Some electromotive force. And what we're looking for is what is the equivalent resistance of the circuit, and then what is the current through each resistor. Okay, so let's start this off with the series example. We've got in this one, let's just draw it this way, a 24 volt battery, and then we'll have in this one here just two resistors coming around. This is 100 ohms, and this one is also 100 ohms. So how do we go about solving for the current through each of these and what the equivalent resistance is? Well, let's start off in this one where, if we're thinking about this, we know the current as it comes out. We know this current is going to be the same for everything in the circuit. There's no branching points anywhere. It's just one loop. So if we find the current, that will be the current for everything. We can find this current by saying, look, if this is the total current of the system, just one set here, if I can find the equivalent resistance, then I can go and use Ohm's law, V equals IR, by saying, look, I know the voltage here is 24. I'll know the equivalent resistance of the circuit, and that will give me the current everywhere, and we'll know the equivalent. So let's do that. How do we find the equivalent resistance of these two resistors right here? Well, they're in series, so I can just add them up. So 100 plus 100, this is an easy one. That is 200 ohms is the equivalent resistance in our series circuit here. Now if we go back and we use our Ohm's law equation, we can say that 24 volts for the entire circuit equals the current through this entire circuit here, the total current, multiplied by the 200 ohms we just found equivalent. If we divide 24 by 200, we will quickly find that the current in our system is going to be 0.12 amps. I don't know why I put those in parentheses, I just did. Whooshing, whooshing. So that one wasn't bad, right? We found the equivalent resistance. We were able to find amps through Ohm's law. Pretty straightforward. Let's go now and look at the parallel setup. So if we've got a parallel setup, how's this look? Well, let's set up the 24 volt battery again. And then now I've got a 100 ohm resistor here, but then I've also got a branch that has another 100 ohm. And sometimes these branches are hard to look at. Technically this branch starts here and ends here. Sometimes I know that students don't like to look at it when resistors are set up this way. They don't like how one's going across and then one kind of makes this like 90-degree bend. I have found that if you don't like this, then try this instead. You know, here's the 24, bring it up and around, and then have the branch go like this. For whatever reason, having the branch look like this with 100 and 100, it allows students to see it a little bit better. Yes, you're redrawing a lot of stuff, but it's easy to see that this is a node point and that's a node point. So if you're having problems with this, draw it like this up here. These are the same systems. You can move the wires however you want. They don't change anything, but it's just something I've noticed throughout the years teaching this, where if you don't like it, how I have it down here in blue, put it like I have up here in red, okay? But if we take a look at this, we are going to have some total current come out here, okay? That's the total current coming out of our battery. But when it hits these node points, this current is going to split. We think about the river splitting at a juncture, and some of the current is going to come through here, some of the current is going to come through here. We'll call this like I1, I2, or IA and IB, it doesn't really matter. Now, we might have the physics intuition looking at this to say, hey, if these have the same resistance, then they should have the same amount of current flowing through them, okay? And that's a great thought for something like that. If they do have the same resistance, the same current will flow through them, and that's totally on point. That's totally right there. So what we could do here is we could find the equivalent resistance of the system, which we're going to have to do anyways. We asked for it. And then I could break up this total current. Okay, so let's do it that way first, and then we'll take an alternate method here. So how do I find the equivalent resistance of our parallel circuit? Well, the equivalent resistance, we really have 1 over the equivalent resistance equals 1 over 100 plus 1 over 100, because remember these are in parallel, and then I need to get rid of this 1 over, I need to take 1 over that entire quantity. So what we actually find here is that our equivalent resistance in this case is going to be 50 ohms. And we know that's true because 50 is less than our smallest resistor, which is 100, and that's what we're going to get out of this. So our equivalent resistance is 50 ohms. So what we could do now if we wanted to is we could say, hey, just like before, let's use Ohm's law. We could say V equals IR. We could say 24 equals I times the resistance of 50 ohms. And this would give us a current here equal to 0.48 amps. But we need to be careful. We need to be very careful here. This current we just found, this is the total current. This is this current right here. Now our physics gut tells us, hey, we can split this up. We can just take half of it because these are equivalent resistors. 0.24 is going to go here, 0.24 is going to go here. But what if they weren't equivalent resistors? How would we do this in that case? Or how could I solve for this current first? Well, instead of finding the equivalent resistance and then using Ohm's law and then splitting it up into the 0.24s, I could do this. I could look at just this branch of the circuit in blue here. And if I look at just that branch of the circuit and I use Ohm's law, what I could say is the following. I can say that there is a voltage drop of 24 volts. 24 volts starts here, and when I get back, I'm at 0. So there's a voltage drop of 24. That has to equal the current through that branch multiplied by that resistance that it's going across. And there's only one resistor here, so that's just 100. Well, 24 divided by 100 gives us a current of 0.24 amps. If I do this for the other branch, same deal, 24 volts equals the current multiplied by 100, because that's the only resistor here. I'm going to also see that the current through the second branch is 0.24 amps. And we should hopefully notice now that if I take the two branches, I1 and I2, so this is I1, this is I2, and I add them together, well, 0.24 plus 0.24 is going to give us the total once again. And we know that has to happen because when this current comes back together, it's got to be the total current. You have that much current in the system, you can't lose it, it's got to go somewhere. So you could approach this problem either way. You could do the equivalent resistance of the whole thing, find the total current, and then break that up. I like to do it this second option where I say, look, here is a nice branching path. Here's what I know about the current, or here's what I know about the voltage. I can find the current, I know the resistance, and I can work from there. Okay, but whatever floats your boat, there's a lot of ways of thinking about this. We'll see in our next example, which is even more complicated, how you can kind of take some shortcuts when thinking about breaking up parallel series. You kind of do a ratio if you only have two things there, but the parallels are a little bit more complicated than the series circuit here, but it's nothing too crazy. Okay, so we've got one more example to do with this, and then some practicing on our own, but for right now, we are finished. So adios everybody, and you all take it easy.